All right, guys, Mr. Antonucci here, and in this section, we're going to talk about the natural logarithmic function and integration. So in this first video, we're going to look at a couple examples on how to use the log rule for integration to integrate rational functions. So the differentiation rules will start with there because integration is reverse differentiation. So for natural log, the integration rule is the derivative of natural log absolute value of x is 1 over x. Let me switch my color here. And then for natural log absolute value of u, where u is a function, it's going to be u prime over u. Okay, so with that, we have a theorem, which is the log rule for integration. So in this case, the integral of 1 over x dx is equal to the natural log absolute value of x plus c. So this should be absolute value of x plus c. And if u is a function and you have the situation 1 over u times du, then it's going to be natural log absolute value of u plus c. This alternative form of the log rule might look a little more explicit for using substitution, where you have a u prime over u form for that. Okay, so we want to look at some examples for using the log rule for integration. So we'll start off with a basic one here, integral of 2 over x dx. We can factor that 2 out and write it as the integral of 1 over x dx times 2, which is 2 times natural log absolute value of x plus c. And because of the power property for logarithms, we can rewrite this as natural log of x squared plus c. And the uh, absolute values are unnecessary in this case because x squared cannot be negative. Remember the property, if you have a times natural log of b, you can write that as natural log b to the a power. That's all we did. Okay, and again, we took the absolute value off because they're unnecessary. If you had left them on, it wouldn't be wrong, but it's just unnecessary and kind of redundant there. So let's look at another example with the log rule. In this case, we're going to look at a change of variables. So for this one, if we let u equal 4x minus 1, then du is equal to 4 dx. Notice there's no 4 in the integrand to go with the dx. So if I multiply by 1/4, so 1/4 du equals dx, then I can make the substitution. 1/4 integral 1 over u du, which is equal to 1/4 natural log absolute value of u plus c, which is 1/4 natural log absolute value of 4x minus 1 plus c. Okie doke. Pretty cool stuff there. This next example is going to use an alternative form of the log rule. So when we do this, we're going to look for quotients in which the numerator is the derivative in some way, shape, or form of the denominator. So here's an example. We want to find the area of the region bounded by the graph of y equals x over x squared plus 1. I have it pictured right here with the x-axis and the line x equals 3. So this region here in kind of a pink color. So to set this up, we can write the definite integral that represents the area of the region. So that's the integral from 0 to 3 of x over x squared plus 1 dx. In this case, if you let u equal x squared plus 1, then du is equal to 2x dx. And adjusting for the 2, we have 1/2 du equals x dx. Okay? So this would be the integral of du over u times 1/2, which is 1/2 natural log absolute value of u, which is 1/2 natural log absolute value of x squared plus 1. Then I'm going to put the 0 and 3 on because I back substituted. So since the 1/2 is multiplying the natural log, I can write it as 1/2 natural log of 3 squared plus 1, which is 10, minus the natural log of 0 squared plus 1, which is natural log of 1. Natural log of 1 is 0, so this is just equal to 1/2 natural log of 10. Okie doke. Now, we can put that exponent up there as a 1/2 and rewrite this as natural log square root of 10. Okay, just different forms. You don't have to change it. You could have left it as 1/2 natural log 10. By the way, if you dump that into a calculator to 3 decimal places, it's 1.151. And if we look back up at our graph, if we make a big, it looks like a square, but because of scaling, it's actually a rectangle. It's 3 units wide by 1/2 a unit high, and 3 times 0.5 is equal to 1.5, but we have all this missing. So I know my area has to be less than 1.5, and according to the decimal value, at least makes sense for this problem. Okay, so the area is about 1.151 square units. Now, in this last example for this video, I want to run through 4 examples where we're recognizing the quotient form for the log rule. Okay, so for this first one, if u is x cubed plus x, du equals 3x squared plus 1, and that's exactly what we have here. So it is that u prime over u form, and we can go straight to the answer, natural log absolute value x cubed plus x plus c. For this next one, it may be a little tricky to see it at first, but secant squared over tangent x. If u is tangent, then du is secant squared. Sometimes with trig functions, you have to rewrite them in terms of sine and cosine and cancel stuff. But here you can see that secant is the derivative of tangent. So that's really that u prime over u, no adjustment necessary. So this is natural log absolute value of tangent x plus c for that one. Okay. So now let's look at the third one here that we have. The integral of x plus 1 over x squared plus 2x. So in this case, if u is equal to the denominator, x squared plus 2x, du is equal to 2x plus 2, which you can factor a 2 out. And you see I have the u prime here and the u, but I have this factor of 2 that's going to need to be accounted for. This is going to introduce a 1/2. So this is like equal to 1/2 the integral of u prime over u du, which is equal to natural log absolute value of x squared plus 2x plus c. Don't forget that 1/2 in the front there. Okay, so because the derivative was actually twice what the numerator is, there had to have been a 1/2 there to cancel it out. I kind of think of it like that. All right, and then the last one I want to look at for this video is integral 1 over 3x plus 2. Here, the choice of u, 3x plus 2, then du is equal to 3 dx. There is no 3 there. So one way you could actually think of this is if you multiply by 3 and multiply by 1/3, you can get it to work out. So what I'm saying is if there was a 3 there, okay, there would have to be a 1/3 out front here. And then the 1/3 and the 3 would cancel and, reduce to the 1 that was already there. So this is 1/3 integral of u prime over u, which is going to be 1/3 natural log absolute value of u, which was 3x plus 2. I'm going to squeeze my plus c in there for that one. Now, with antiderivatives involving logarithms, it's easy to obtain forms that look quite different but are still equivalent. So if we go back up to this example here, um, where we had 1/2 natural log absolute value x squared plus 2x, we could rewrite this as natural log absolute value x squared plus 2x to the 1/2 plus c. And 1/2 is the same as the square root. So this would be natural log square root x squared plus 2x plus c. So that's it for this video. Hope that was helpful. We're going to continue the rest of integration with the log rule in the next video, and then the video after that, we're going to look at some examples of trig functions. All right, guys, hope that was helpful. Reach out if you have any questions. Take care.